My background is high energy physics, for which I did a stint at CERN and analyzed lots of high energy data. So I'm very familiar with a lot of the stuff at the conference. I spent almost 10 years at Argonne National Lab looking at more data from a theoretical point of view. And that kind of trained me to look at data. And I want to preface all of this because I learned to look at things from a physicist's point of view, which is I get interested in particular problems. I left physics and went to work at Bell Labs and Motorola, where I did software development, which was a far cry from doing physics. And in those jobs, as well as a startup, and in those jobs, I got involved with doing strategic planning, among other things. I ran groups, and in strategic planning, we had to solve problems like, how come you were 2 years late delivering the software? And yeah, well, we really were 2 years late, and it was a problem. What I learned from that exercise after hiring a consultant that was trained at MIT by Jay Forster, I learned that problems are not normally solved by stochastic means. We had a group of 500 people stochastically trying to explain why we were 2 years late. They failed. Actually, they were given an interesting choice after our exercise. They could either become developers or leave. So I have a real strong, firm foundation that you understand problems by understanding what happened. And we understood why we were 2 years late by actually looking at data and looking at processes. And we learned to look at complex systems the way Jay Forster looked at complex systems, which is look for the processes, look in the small. The small helps you understand what's really happening. The problem with looking at the small is human beings, us, are not good at collecting all the information together into a picture. Actually, that's why we're at this conference, right? Right? Because we have to visualize that small as it goes into the very large. Well, here's a picture of the small. Let's see if I can get, there we go. This is not a picture of the Earth as seen 2,000 years ago. The picture of the Earth as seen 2,000 years ago is that the Earth is flat. We all know the Earth is flat. Okay, anybody like to go sailing? I love to go sailing. If you go out on Lake Michigan, it's flat. Okay? How do we explain flatness? We explain flatness by looking at our locale and saying, everything around me, as far as I can see, is flat, therefore the Earth is flat. Okay? Wrong, but almost right. Every place around us is flat. That goes back to my software development experience. We all understood what the small effects were. We just didn't know how to piece it together. If I go sailing around the world, I can't use one chart. I have to use lots of charts. And I need a theory for how these charts fit together. If I have a theory for how the charts fit together, I go from flat to round, okay? Now, if I ask the question of you, what's the shortest path on an oblate spheroid? Is it a great circle? How many people would say yes? Right, it's not. That's what it is. Okay, you can see it's not at all a great circle, right? I just used different colors so you could sort of see it, but that's one, or a portion of one geodesic. Another example of our intuition of the way things are doesn't work. I want to apply those ideas to making decisions. Okay? In order to apply the ideas to make decisions, I have to change somewhat the conceptual base. Okay? Now in business, what it means is I don't talk to managers, I talk to developers. Because they understand the conceptual base. They understand the flat part of the world, okay? The flat part of the world, which is not stochastic, is kind of like the Earth what we want to figure out in decisions is if I start in a known place, okay? Like in a project, I start at a known position, I have all my resources, I have all my developers, and I start moving forward. I want to know where I'm going to be at some future point in time, okay? So that's, I'm going to need some principle of how to get there. Something like the Earth, I need some principle of least action. I got interested in this because I saw these problems and I said, hey, this looks just like a physics problem. I've seen these problems a lot. In physics, we talk about the principle of least action. Well, does physics have any applicability here? Well, first of all, I am a real believer that decisions occur in the real world. They occur in time and in space, okay? And then in that sense, they're no different from any other physical process. However, there are a lot of variables, you say, right? So many variables, in fact, that there's no way we can think of this. This is the senior manager saying, we're late and I don't have to explain it to the customer, sorry. Wrong. You do have to explain it. There aren't lots and lots of variables. We actually have great insight on decision making in terms of characterizing the variables. In physics, you don't have to characterize all the variables, okay? If I fly a jet plane, I don't need to know every piece of information about every atom that's in the air. I only need to know those things that are important, the active variables. Von Neumann and Morgenstern in game theory identified what are the most important variables for making decisions, be it economics, be it games, be what anything to do with human processes. It's to identify what the pure strategies are. And he went through a rather elaborate detail to show that you can always do this, whether the game be chess or poker or the stock market, you can do it. Okay? It may be hard, but you can do it. That's the space we live in. It's a different space than what physicists talk about if they're running a car down the highway, but it comes from the same notion that we live in the real world, we have to identify the active variables. Once we identify the active variables, we're in pretty good shape. Second, we have to identify any symmetries of the problem that are important, okay? That's kind of you may not think of it this way, but as a physicist, I have to think of it this way. But is it important to us in making decisions to know what these symmetries are? And I say yes. Most of us are aware that in the real world today, we hold up the idea of an Adam Smith that says we all should be selfish in our behaviors. That's what determines decision making. We should look at the short term, we should do what's best for the company, we should think about our quarterly profits. That's what we got to do. Don't worry about the big picture, don't worry about anything else. Adam Smith told us this is it, and everything will work out all right for everybody else. Okay? My last name is Thomas, I got to be a doubting Thomas, right? So I went and I read Adam Smith. Not all of it, that's long. But I read the part where he quoted this thing, and I found that he didn't quite say what I just said. He said something very similar. He said, he was a very moral guy. He said, there are certain assumptions which I hold to be true that always must be there. Like if I do a transaction, I make a deal with you. I say, let's do a deal. I'm going to give you money, you give me a product. Okay? You have to honor the contract, I have to honor the contract. That's a symmetry. That's like, it's understood by everybody, I don't have to say it, but a contract is like a code of conduct. It's like good behavior, you got to do this. Code of conduct is something that is there, it's a symmetry, it's outside the construct, okay? If I talk about the weather on the Earth, okay? The Earth is a symmetry, which I normally don't consider, but it's there, right? Okay, I know that the wind comes from that direction, in this hemisphere, at this latitude. It's a part of the discussion, but it's not something I explicitly always consider when I'm doing my fluid equations, right? So I have to think about that. And besides picking the active variables, I also, I'm thinking about a theory which is different from anything that's out there, okay? There isn't, I mean, if I go talk to economists, they say go away, because what do I know about economy? What they do is they give me all the books they ever wrote on economics and say I should read these before I should come back. If I go talk to physicists, they say, what's economics? Why are you doing that? You know, if I talk, you know, actually the people that would listen to me are the people that I worked with, okay, in startups. They're CEOs. They're just looking for a way to do their job better. And if I have a way to do their job better, they would actually listen to me. Before I can talk to them, though, I better have a few examples worked out where I think I know what I'm doing, and make sure that what I just said is all that I need to know. And it turns out it's not all that I need to know. So here's a picture of a kind of problem which I might have in the real world, okay? This is a picture of the stock market about a year ago. It's kind of a nice picture, right? It shows downs, it shows ups. It's normally thought of as a stochastic process, right? Why? Because it doesn't show any nice smooth curves. Nice smooth curves are physics. Bumpy curves are stochastic. Okay? But what does stochastic mean? Stochastic means whatever is happening, whatever I'm going to predict, doesn't depend upon what happened in the past. That's crazy. Okay? But you say, well, I don't know what happened, so I might as well assume, right, that it doesn't matter. Well, it does matter, okay? It mattered to my group that was 2 years late, by the way. Okay, here's some curves. Looks bumpy, right? Okay, this set of curves was computed from Mathematica using differential equations that looked a little bit like Maxwell equations. Okay, with 50 variables, 50, you know, lots of equations, 200 equations. I don't remember now. It's been a long time since I computed it. But it's bumpy, right? Has the same attributes. So bumpiness by itself doesn't say that it's stochastic. It just says it's complicated. This is complicated. Okay? It started me thinking that there are lots of things that are complicated that have causal reasons that we can understand. I said I like to go sailing, right? I love to go sailing. When I'm out on the water, I see this behavior all the time. Every storm looks like this. The water looks exactly bumpy. Okay? And guess what? In a storm, I have a theory of fluids that predicts this behavior. It predicts what happens when the wind gets above a certain strength, so that I not only get waves, but I get waves that break. I get vortices. I get all kinds of interesting chaotic phenomena, all of that coming from a theory that is causal. So, you know, this is my 30-second elevator talk, right? Notice I'm not showing you the equations. I'm not going to. Right. What I want to show you is the value of doing a causal computation. Now, if I just had to do the causal computation, life would be easy, okay? Why is life not easy? Life's not easy because this is not an area of physics. I have to stress that to myself, okay? Not to you. You're not physicists. But to me, I have to remind myself this is not a physics problem where I can go into a physics book, open it up, and say, here's the answer, just copy the results. It's a wrong number of dimensions, and all the properties that I'm looking for have more to do with the theory of games than they have to do with the theory of dynamics. I can learn a few things if I sit still long enough, but I start in the process of going through hundreds of models. I came up with a series of distinctions which you have to add to the conversation. Many of them are motivated from game theory. I mentioned one like the code of conduct. Some are motivated from how the theory works. They don't show up in game theory because game theory assumes that, if I go back to my water analogy, game theory assumes that the lake is flat. And we know the lake is not flat. That stock market picture is not flat, right? So if the world is not flat, then I have to worry about some new ideas, like how strongly a player in a game couples to the game. Okay? So there's something called engagement. There's something called value, okay? Game theory has a concept of value. I had to think about that long and hard because value or utility doesn't show up in this physics way the same way it shows up if the lake is flat. Turns out value or utility is more like it's a payoff. It's a sort of a measure between you and a particular strategy, a strength, how much you value it. But if you carry that idea a little bit further, there must be utilities between any pair of strategies. So you have to work through all of that. So I need some examples, okay? So the first thing I did, by the way, I presented some of these ideas at a complexity conference, and I got, in the audience, like right there, was John Nash. And he didn't go, "You're wrong." What he said was, "What can you compute?" So I started thinking about that. I guess I better really compute, because at the time, I had lots of ideas, more at the idea stage and not the computation stage. So I said, okay, I really need to compute. I had a few things computed last year. It turns out the computations, the sidebar, computations involve, like they do in weather prediction, they involve partial differential equations. Sorry. And there are a lot of them, because there are a lot of strategies. So the equations are rather complicated, so I wanted to pick some simple examples. One of the simplest examples I found, and I found a lot of people at the complexity conference, are all from the military. So guess what? My first example is going to be a military example, okay? I had two armies, red and the blue, because they always call them red and the blue. And one army, the blue, defends itself, defends two installations. The red army attacks two installations. So they each have two strategies, two sort of pure strategies. Attack the big one, attack the little one. Defend the big one, defend the little one. Okay, so that's four strategies. That's already was a little too much for me, my ability to compute. And also, Mathematica on a laptop, it's it's fast, but hello guys, Mathematica guys, I need help. I need more computing power. The cloud may help me. I reduced the number of strategies by one, okay? Because I said, in game theory, nobody ever worries about sort of what the sum of the strategies are. It doesn't have a lot of meaning, okay? Just assume the game goes forever and the sum doesn't mean much. So I took that as a code of conduct. So I took it out. That left me with three strategies, which I cleverly called U1, U2, U3, okay? For absolutely no good reason. U1 is the strategy for the defender. It measures the frequency with which it's going to defend its two installations. U2, guess what, is the strategy for red to attack the two installations. So far, so good. That's about all game theory would say. Even though I made a simplification for a code of conduct, it leaves me with a strategy that's very new. It says, it does matter how intense each player plays the game. That's U3. It's not determined by red or blue by themselves. It's a mixture of red and blue. Okay? And I don't know if I can make this a little bit more obvious, but you can see that, well, U1 and U2 increase over time forever. That's kind of the idea that in this world of strategies, what I mean is preference, and a preference that increases in time means I pick a strategy with a constant rate all the time. That corresponds, if it was truly a straight line, that would correspond to the Nash equilibrium. Okay, that would be very simple. So you see something that's not Nash equilibrium, it's that things alternate around the strategies, around the equilibrium. But I picked an equilibrium solution as kind of as an input to this. It doesn't mean that it's always going to work this way. Now this mixture strategy of engagement doesn't grow in time at all. But it's bounded and is part of the oscillation. But you see, you get some interesting pictures. Now, the other aspect, which is totally key to having an understanding of causality, is that things have to be connected. I don't know, there's an entire theory of network connectivity by Barabasi. It's a way of saying, in a causal world, we're all connected to each other, that what I do impacts you. If in a market, what this company does affects that company. If everybody starts building widgets, we all build widgets. We all go that way. If everybody starts doing something else, we all go that and do that else. Okay? So we're connected to each other, and we have to have some term that measures the connectivity. I call it pressure. That's because I'm a physicist. Okay? Mechanical engineers call it stress, like on a bridge. Okay? It also has some psychological thought, right? I don't think it does, but oh well. You can see that pressure, which is the maximum, is sort of constant, but there's some ripples, okay? Now, the ripples are important, okay? This is not like the answer to every problem, any more than if I look on the lake, it being flat as the answer or having small ripples as the answer. Okay? Here's the part where you have to think differently. It is the part which I didn't learn from physics, I learned it from systems dynamics about how to deal with complex systems in management. The way you look at a company is you ask the company, what does it do, steady state? And then how does it respond if you do something different? In our case, we were 2 years late because the steady state was the customer would just come in every two years, give us a set of requirements, and we would deliver in a year and a half, whatever it was. The customer came in and did something unusual. Halfway through the process, they asked for 50% increase in requirements. That was a ripple effect that rippled through the development cycle. This is an example in the model of the ripple effect. I constructed a ripple which started and ripples through. Okay? It's the same example that says in weather, if there is a storm, it has a ripple effect all the way through the country. Okay? That's what a causal theory does, is it allows you to study the impact of ripples. I currently teach engineering, and from the engineering stuff, I learned how to write the equations and deal with it, because this is a common problem in electrical engineering, which is, like I teach microwaves, okay? And what I want to know is, what does a microwave do for an arbitrary input? I don't study arbitrary inputs, I study steady state and harmonics. And from the steady state and harmonics, I use superposition to build up the full answer. Okay, so this is what we're doing here. In this case, looking at steady state and harmonics. The second example I want to give is one, let's see how am I doing? Okay, second example I want to give before I finish is a classic example from game theory that doesn't work in game theory. The classic example is that of two prisoners who have done something wrong, who are told that if they both confess, the book gets thrown at them, but if one confesses and the other doesn't, it's even worse. However, if neither confesses, they go free. So what would two law-abiding prisoners do? They keep their mouths shut, right? Obviously. Okay? If they were in the mafia, you know they would keep their mouth shut. Okay? What is keeping their mouth shut called? It's called a code of conduct. What does game theory not have? A code of conduct. What does game theory predict? It predicts they confess. Hence, it's a paradox. So, just for ducks, I set up the payoffs as game theory would set it up, set up a stress the way I would set it up, and started computing in time what the payoffs would look like as a function of, in this case, I only have one variable, which is active, which is the relative engagement of the two players. I got rid of all the other pieces, so we could just look at that one aspect. And I'm looking at time. So there's my two variables. And you notice that my payoff is not constant. Nor, by the way, even though I put in simple ripples, nor is it ripply. It has holes. Okay? The fact that it has holes is an example of the storms, okay? The chaotic, the start of, I think, the start of chaotic behavior. Okay? Showing that this is the kinds of things you would expect. And in addition, there are some other utilities, okay? In this case, the utility function, which I call a metric, between time and itself, which doesn't have any place at all in most theories, including Newtonian physics. But it does have a place in Einstein's theory of gravity. And in Einstein's theory, this would be the gravitational potential, and things would fall into those holes. Okay? What it says, I set the situation up anti-game theory. I said, how do the stresses compensate each other if the two players keep their mouths shut? Well, there's clearly stresses, there's clearly a code of conduct, and there's clearly some, depending upon your initial conditions, some interesting behaviors of holes they can fall in. So, what are the conclusions? Okay, by no means has this been a long enough talk to give a logical argument. Okay, I do teach ethics, by the way, and I teach about logical arguments. This is not one of them. But I hope I have suggested to you as a possibility that you can have a theory that would describe the stock market picture at the very beginning, that is dynamic, that's quantitative, because these are quantitative curves, can be applied to data. By the way, it's a theory that can be wrong, which is a necessary ingredient of any theory, any physics theory, right? So most of my time saying why it's wrong, and then, rats, it's working, right? Physicists have a totally backwards way of thinking about this, right? It's predictive. It looks at frequency of things, not as stochastic, but as we don't need to know why a person made certain decisions. We just need to know that they sometimes choose something more often than they choose others, and that frequency can change in a causal way over time. I would plug Mathematica to give me more tools to do coupled partial differential equations that are elliptic. That's a problem for me. They have a theory of lines which works, and it works very well, but it would be nice. You can see my web for more details, and my last little bit is one thing for the future to think about as an initial application is, in looking at markets, businesses focus primarily on quarterly profits, okay? Those would be the short cycles, okay? Whereas businesses that stay around for long periods of time, a lot of the Japanese companies stay around for 100 years. Look at the long cycles, okay? If you want an accurate picture of some of the market cycles, you need to incorporate both the short and the long cycles. So that I think would be one of the real interesting next steps to investigate.